Allora, BIMP, questo BIMP, chissà, scusate, c'è un BIMP, ma non so questo BIMP. Ho fatto BIMP, ma non so. Ok. So, let's restart from where we arrived last time. So, what we are doing is we are trying to develop a new technique for solving partial differential equations. For the moment, we are concentrated on a specific type of equations which are time independent, but after the generalization to time dependent problems, the problem of diffusion or the problem of the waves will be relatively straightforward. And this technique is what is called finite elements. So, as you recall, I mentioned that this finite elements technique is based on three ideas. The first idea is the one that we have discussed last time, and it corresponds to rewriting the boundary value problem in the version in which we have a differential equation with explicit boundary values. So the version we started with, okay, let's say something like this, or even the time independent part. So, I mean, instead of having this full equation here, maybe we concentrate for a moment on the time independent part, equal to some function f of x. Let's see a moment where we wrote explicitly this type of equation somewhere here, for instance. Okay, this is an example, a simple example of the type of equations we are discussing for the moment. Okay. So this is the so-called strong version of the boundary value problem, in which we have a differential operator, we have an homogeneous object, our function f, and boundary conditions. And what we have demonstrated last time is essentially that one can reformulate that problem. The problem there is find the function u that satisfies the differential equation and satisfies the boundary conditions. This problem can be rewritten in another form, which is the one that we have seen essentially down here. Okay. So this other form is a form in which we are instead saying, okay, instead of solving that differential equation, let's consider another problem. The problem is we are looking for the function u. U is the quantity that we want to determine. And this time we claim that the u is a function such that this relation here, that I have written as an integral, holds for whatever test function v, for whatever test function v. So as you recall, this rewriting of the problem is based on the fact that if the operator in particular is symmetric, it is possible to introduce a sort of physical interpretation of the differential equation in which we have potential energy, and we have demonstrated essentially that the stationary solutions of the differential equation are also minimizing the potential energy. And I also mentioned another way of formulating the same idea, which is the idea of virtual works. Essentially corresponds to the fact if you have the mechanic of just one point, the force is just minus the derivative of potential respect to x, let's say. And if you are at the minimum of your potential, then, of course, since the derivative there is 0, you can also say that whatever movement you make around that minimum position corresponds to 0 work, because, of course, it is the force which is 0, and this can be generalized in more than one dimension, and to this situation, which is not the mechanics of one point, but is more the mechanics of a finite object, so field theory, if you like. Okay, so this is nice. It was the first ingredient in this finite elements technique, but is not extremely useful by itself in helping us to solve the problem, to get the solution, to get the U. There are two other ingredients. So the first point that we can stress is that obviously we have not gained a lot by performing this transformation, because still we are dealing with having to determine this function U is a continuous function. And so it is one function inside a class of infinite other functions, and we don't know how to reduce for the moment this problem from a problem in which we have an infinite number of degrees of freedom. I mean, for instance, let's say that U belongs to some L square space, but L square is a space with infinite dimensionality. So how do we move from that problem, the problem of having still an infinite number of dimensions, degrees of freedom, to a problem that we can solve, for instance, numerically? So here comes the second ingredient. The second ingredient is a little theorem that allows us to clarify under which conditions we can reduce the problem from a problem of finding the solution U in a space of infinite dimensions. We can reduce that problem to finding the solution to a space of finite dimensions. Of course, it will be an approximation, but what we have to check is if our approximation is at least self-consistent. If the approximation that we are considering is the best approximation within a certain subspace of solutions. Are we really writing this new equation that we are going to write? Is it really the best equation that we can write if we want to find the best approximation to the exact solution approximated within a finite dimensional space? This is the question. So, in order to understand this question, let me discuss a little theorem without really demonstrating it, because I don't think it's particularly useful, the demonstration. So the little theorem is a theorem of linear algebra. It is called the projection theorem. So this projection theorem essentially discusses the following problem. So suppose that we have a space V, and this is a vector space. Okay, so it means essentially that we have defined in particular a scalar product inside this space. Okay. And after we have a subspace, let's call this subspace omega, and this is a vector subspace of V, in the sense that also inside omega we have defined a scalar product which work inside the subspace. And the question is, suppose that we have a vector V belonging to the initial space V. And is it possible to tell that there is, and is unique, a vector U belonging to the subspace omega, so that U is the best approximation to V within the subspace? The question is it possible to find a vector U that we claim to be the best approximation to the initial vector V restricted to belong to the subspace omega? As you can imagine, this is really the question that is relevant for us, because as I was mentioning, we have written that equation, but that equation needs to be solved, let's say, in L square, which is an infinite dimensional space. So we would like to write another equation where the ingredients are limited to live in a certain finite dimensional subspace, but we want to be sure that the equation that we are writing is at least consistent. The solutions of that equation will really correspond to the best approximation to the solution of the initial equation if we restrict ourselves to a certain subspace. So is it possible to formulate this problem in a correct and formal way? Yes, using this projection theorem. So I'm not demonstrating it, but there is a demonstration of the book, but it's honestly a little bit boring. And so the first point is, what does it mean? What does it mean that U is the best approximation to V within the subspace? Well, we can consider, first of all, we have defined a scalar product. And for the scalar product, we can define a norm. Okay. So if we have a norm, we can consider the norm of V minus U, of the distance from V to U. And essentially, to tell that U is the best approximation to V within this subspace means that the norm of V minus U corresponds to the minimum of the distance between V and a generic vector omega if we take whatever vector omega inside the subspace. So what I'm saying is that my definition of best approximation is U is the best approximation to V if the norm of the distance between V and U is the minimum of all these distances if I take omega as whatever vector inside the subspace. Okay. And the point is that, yeah, one can demonstrate that it exists and it is unique, this vector U, which is the best approximation to V, restricting ourselves to the subspace. But what really we are going to use is a little property, which is quite nice. And one can demonstrate that this definition, I mean, the previous line is, what does it mean that use a best approximation to V? We can demonstrate that this is equivalent to the following. If we take the scalar product, so recall we have defined the scalar product inside these spaces. This is the minimum request that we have to impose, but the scalar product is defined. So let's take the scalar product V minus U with what? With a generic Z belonging to the subspace. And we say that this is equal to 0 for all Z belonging to the subspace omega. So what I'm saying is that this second equation is equivalent to the previous one. To tell that U is the best approximation to V within the subspace is equivalent to say that the difference between V and U is orthogonal to whatever vector within the subspace. Intuitively, it's quite clear in the sense that we have, let's say, a certain space of higher dimensionality, and after we consider a subspace of lower dimensionality. So what can be the best approximation? As this theorem is telling, is the projection. So essentially it means that all the components of the initial vector that I called V, that are not, I mean, the projection is U, corresponds to the situation in which all the components of V, which are not present in U, are orthogonal to the subspace. Imagine that I have a two-dimensional space and I project it onto a b-dimensional, so it's really a projection in the ordinary sense, and the best approximation is this projection. So it means essentially that the components of the original object that do not belong to the approximation U are orthogonal to the subspace, are orthogonal to that surface. Okay. It's possible to demonstrate that these two definitions are essentially equivalent. The first one is the definition by itself. The second is not a definition, but one can show that is equivalent to the previous one. Okay. So essentially what you do at that point is to take an approximation to V within the subspace and to expand your approximation, your U, on a basis which is spanning the subspace. Okay. And okay, there is the demonstration of the book is in chapter 3, but I would skip it. It's just a little bit. So what we are going to use is essentially this second property, in the sense that we will check explicitly in a moment that our approximation corresponds to writing a solution, to writing an equation. The solution of that equation will satisfy this second equation with the exact solution of the original equation. So at that point, we can claim this is really the best approximation to the solution of the original equation within the subspace. Okay, so just keep in mind that these two things are essentially equivalent. Okay. So let's now go to this technique which is called Galerkin technique. And let me remind a moment again what we are doing. What we are doing is essentially to tell that the original problem, where is gone, original problem, okay, we recall, and this other problem here are equivalent. Okay, so let me rewrite a moment the two formulations so that it is clear what I'm speaking about. So, okay, the original formulation you recall the formulation in terms of this weak form corresponds, let me write it again just a second, corresponds to saying that the integral between 0 and L, k of x, du over dx, dv over dx integrated dx is equal to integral between 0 and L of f of x, v of x dx, and this is true for whatever v belonging to the same space v of the solutions. Okay, this is our weak form of a boundary value problem. Okay, we have demonstrated that this form here is equivalent to the strong form. Okay, so let's go back therefore to this Galerkin. So the problem here is that this space is too big, it's too large. So we want to restrict ourselves to a subspace. The first point is, let us introduce a little notation. This quantity here, this integral between 0 and L of k of x du over dx, dv over dx integrated dx, let me call this a of u and v. This is a functional, okay? It takes two functions, u and v, and it provides a number. And okay, this functional is bilinear in the sense that it is linear both in u and in v. And there is two other interesting points. It is clearly symmetric. A on u and v is equal to A of v and u. And another point is that A of u is equal to 0 only if u is equal to 0. This last point is easy to check. I mean, if I put here u and u, of course, this quantity here is just the integral, is just the integral between 0 and L k of x du over dx squared integrated dx. K of x by definition is positive. This is positive. So in order for this to be equal to 0, du over dx must be equal to 0 everywhere, but we are for the moment working in a subspace in which u of 0 is equal to u of L is equal to 0, and therefore if the u over the x is just 0, u is a constant, and therefore u is identically 0. So this means essentially that this quantity A that I have just defined, I can use as a sort of scalar product. It satisfies my definition of scalar product in the sense that a scalar product must be symmetric, bilinear, and it is possible to define a norm. The norm, as you recall, the norm of a vector is the scalar product, norm square of a vector is typically the scalar product of a vector with itself, and this property that we just discussed tells us that the norm of a vector is equal to 0 only if this vector is 0. So altogether, we can claim that U defines a scalar product. Okay. Recall that the little theorem that I discussed a moment ago was essentially telling that the equivalence between those two formulations can be demonstrated if we have defined a scalar product that works both in the original space and in the subspace. Okay, so we take now this as our definition of scalar product in particular. So now instead of having, this equation here can be simplified. I can also introduce the notation FV that essentially is this also sort of scalar product that I defined here. F and V is this integral here. Okay, so I can write that equation. I can write that equation in the form A of U and V equal to F V, and this for whatever V belonging to the space V. So the weak formulation of a boundary value problem is that once I have defined this scalar product A of U and V, then this equation holds for whatever V belonging to the original space big V. Okay, so the U has to satisfy this equation. So I've just rewritten it, and I've just noticed that A satisfies a certain condition that allows us to say I can build through it a scalar product, a norm, whatever is needed. So now what I am claiming is that if I consider a subspace Vn, so Vn is a subspace of V, and if I take a generic Vn vector inside the big Vn subspace, then I can write the following equation. I can write, let's say, A of Vn and V equal to F, sorry, okay. A of Vn and V is equal to F and V, and this time this is true for whatever Vn belonging to the subspace Vn. Okay, so notice the notation is slightly awkward in the sense that we are now calling the approximation to the solution U, instead of calling it UN, we are calling it Vn, but honestly doesn't look extremely smart. The problem is that we will use UN for another quantity that will be the projection of Vn on a certain basis. So, okay, let's assume this notation. So what I'm saying is this is the original equation, and we have written it, of course, in the original space. Now we restrict to a subspace, and we say, okay, let's write this new equation here. This new equation clearly defines another object, which is Vn. Okay, so everything in this new equation belongs to the subspace Vn. The test function belongs to the subspace, and the solution belongs to the subspace. Okay, all of that belongs to the subspace. Okay, also V belongs to the subspace. V and Vn belong to the subspace. Okay, so the question that we are addressing is this really the solution, the Vn? Is this Vn the best approximation to U if we restrict ourselves to the subspace? This is the question, okay? So we have the original equation written in the full space. This equation here written in the subspace. And we ask ourselves, suppose that we solve this equation. And in this equation, the ingredients are written in the subspace. Okay. So is the solution, the Vn, the best approximation to U if I restrict myself to the subspace? Because there is some sort of arbitrariness in the way in which I have rewritten this equation, original equation, in the subspace. And the answer is yes. It is quite easy to check because let's subtract these two equations. So if I subtract the two equations, I write A of U and V minus A of Vn and V equal to 0. And of course, I know that this is true. This is true for whatever V belonging to the subspace Vn. Because the first equation is true everywhere in the big space. The second equation is true within the subspace. So if I subtract one from the other, I know that the second equation is true within the subspace. Okay. But at this point, I can just make use of the linearity of A, and I can write that A of U minus Vn, V, is equal to 0, and this is true again for all V belonging to the subspace. So this is exactly the formulation of the little theorem that I have written without demonstrating it before. Let me just check again. The little theorem was somewhere here. So the little theorem was telling there is a sort of definition of what it means best approximation. Best approximation is the distance between an original vector belonging to the original object, that this original vector, I was calling it V here. The distance between V and U instead is approximation, okay? U is the best approximation to V if it is the minimum of this distance. But this is equivalent, I said, to telling that V, exact solution, so to say, minus U, approximation within the subspace, this has to be orthogonal to all the vectors inside the subspace. V, exact solutions, minus the approximation, orthogonal to all the vectors within the subspace. We go down here. The exact solution was U. U was the solution of the original equation. U minus Vn, solution of this equation here, orthogonal to V, where V is whatever vector within the subspace. So we have essentially demonstrated that this way of writing the equation, this way here, is consistent in the sense that the solution of this equation, that is an equation written entirely within the subspace Vn, is really the best approximation within the subspace to the solution of the original equation. I'm not making some, I'm not losing pieces, I'm not arbitrarily truncating it. What I'm getting is really the best approximation within the subspace. Does it make sense to you, all this for the moment? Is okay up to now for everybody? Yeah? Also people from home? Maybe. people from whom...
Yes, it's clear.
Okay, fine. So, okay. So let's try now to understand how to use this idea. So the idea is we are able to write an equation, essentially this equation here, that is similar to the original equation, but this time we know that we have restricted ourselves to a certain subspace that we are comfortable to work with. In practical terms, how can we use this idea? So in practical terms, it means that, as I was mentioning when we discussed the theory of projection, we need to introduce a basis which is spanning the subspace. And so suppose that we introduce a basis, let's call this basis a basis of phi 1, phi 2, phi n. And this is a basis for Vn. Okay. So what does it mean that we want to find a Vn satisfying this equation for whatever V belonging to Vn? Well, it means that since this whatever in particular refers to V, okay, it means that since V can be expanded on the elements of the basis, it is enough, whatever V can be written in terms of Phi1, Phi2, and Phi n. So in practical terms, it means that I have to check that this equation here is satisfied for each of the elements of the basis. So it means essentially that I have to find a Vn such that A of Vn phi j is equal to F phi j for j running from 1 to n. So the original problem is now reformulated in this way. Find a Vn such that this equation is satisfied when I put instead of the test function here each of the elements of the basis that I am considering. So you see that this is the moment in which I am really using the reduction of this space, because originally the original equation was very similar, but this V was belonging to, let's say, L square. So I did not know in which way could I be sure that I was checking that this equation was satisfied for whatever V inside the big L square. It was a difficult problem. So instead of solving this difficult problem, I reduced the problem to a much easier one. I reduce myself to a subspace of finite dimensionality, and therefore that difficult problem now becomes a relatively easy problem. Is to find a Vn belonging to the subspace such that this scalar product is equal to this for each of the elements of the basis. Okay. So it is clear that now we can also expand our Vn on the same basis. So we can write that Vn is a sum on, let's say, let me just be careful with the notation, okay? I'll change the notation after. Okay, not particularly smart, but okay. It would have been better to write it here instead of the index j, the index I maybe, but okay, too late. So J running from 1 to n. And you recall it was telling, it seems a little bit strange to use Vn as a notation for best approximation to U within the subspace. Why not to call it Un? Because we use the U for the coefficients of expansions of Vn on the subspace. So now we call these coefficients Uj, Vj. Okay. So let me tell again. The Uj are the coefficients of the expansion of the approximation to the solution within the subspace expanded on the basis that we have assumed. Okay, so that's it. So at this point, we just substitute back there. Of course, this becomes A of sum on J from 1 to n of Uj phi j, and okay, here I have to change the index. Here I used to call it j, let's call it I, phi I, and this has to be equal to f phi I for I running from 1 to n. And finally, I make use, of course, of the linearity of A, and therefore what I'm getting here is something as a sum on J of A phi j phi I Uj, and this must be equal to f phi I again. Okay. So it is clear that I ended up with a linear algebra problem, because I can define a matrix. Let's call this matrix Kij, and Kij is defined as A of phi j phi I, while these other objects here, the scalar product, let's call them Fi. So Fi is f phi I. And at this point, it is clear that I can say that these equations here can be recast in a matrix form as matrix K U equal to, okay, put maybe a vector, is better, equal to F. So what is U? Of course, this U is just U1, U2, UN, okay, and F similarly is F1, F2, Fn. And K, so K is a matrix, n times n. This is a column, and this is a column. Okay. This object here, K, belongs to R and N. Okay. So that's it essentially for the moment. For the moment, what we have demonstrated is that it is possible to reformulate. Notice where we started, where we are now. So we started from a strong boundary value problem written in terms of a differential equation, boundary conditions. We have rewritten it as a weak version of it, meaning that we have rewritten our problem in this way here. And instead of trying to solve this problem within, let's say, L square, we are now saying, let's restrict ourselves to a subspace, maybe a subspace of finite dimensionality, so that we will be able to numerically solve it. And we have checked that, so this was just a change in notation once we have introduced the scalar product A of U and V. And what we have checked is that this way of writing the equation within the subspace Vn is consistent in the sense that the solution Vn is really the best approximation to U if I restrict myself to the subspace. This is what we have checked. At this point, we just expand everything on the basis for this subspace Vn. So we are expanding the test function. At that point, of course, we don't need to refer anymore to this V, in the sense we have this finite dimensional basis, phi 1, phi 2, phi n. So to tell that this is true for this one is true for whatever V belonging to Vn means that I check for each of the elements of the basis and I am happy. So I go back to these equations here. I have to check for each of the elements of the basis, but it's finite dimensionality. And finally, I expand the solution on the same basis, and I end up with a linear algebra problem. This matrix K is the matrix of the scalar product of the elements of the basis. U is the solution, and F is this other sort of scalar product of F on each of the elements of the basis. Okay. So how does this technique compare with the technique of Fourier that we have discussed before? You recall that the technique of Fourier essentially corresponds to solving the initial problem, the strong boundary value problem, and to find eigenfunctions and eigenvalues. So essentially, to find the eigenfunctions, if we are able to, it's very nice, because since our differential operator is symmetric, the eigenvalues are real and the eigenfunctions are orthogonal. So at that point, we can use the eigenfunctions to generate a basis, and this basis is the best of the possible basis because it's made of vectors which are already orthogonal. I can even orthonormalize and everything can be expanded, and we are very happy. Which was the problem there? In general, it is not easy to compute the eigenfunctions. Not only in general, there is not a way of computing the eigenfunctions analytically, but even numerically, it can be very time-consuming to compute a certain number of eigenfunctions. The problem of getting the eigenfunctions is numerically not much different from solving that equation by using some other numerical technique. So there is not a big advantage. So the Fourier technique is mostly useful if it is possible to find, let's say, analytically the eigenfunctions and the eigenvalues. In most cases, it works, like I say, as a spell, is magic, okay? It's simple and effective. That's why in the old books of partial differential equations, I mean books written maybe 100 years ago, they were essentially discussing only the Fourier technique because it was the only practical thing that one could do was to resort to some simple problem in which it was possible to find the eigenfunctions, etc., etc. So the problem with the Fourier technique is can be very tough to find the eigenfunctions and the eigenvalues. So now we have resorted to another technique, and in this technique, so notice that in principle, the Fourier technique, one could say, okay, I understand that it's not easy if I cannot evaluate, if I cannot find analytically the eigenfunctions. Still, suppose that I am willing to spend the time needed to compute the first 10 eigenfunctions. Okay, so if I get the first 10 eigenfunctions numerically, let's say, then I can use them because, of course, these eigenfunctions are orthogonal. Generally, it's trivial to normalize, and I get my solution, expanding the solution on a basis of the first 10 eigenfunctions. So there I spend my time and money in computing the eigenfunctions, but after, if I have computed them, I proceed rapidly. What happens here? So in this case, we are not trying, so to say, to compute the eigenfunctions. We are looking to some basis phi j. Okay, so this basis phi j, how do we choose it? Well, now I provide a couple of examples. Okay, in general, we can use a basis that is made of functions which are relatively simple, and I can therefore compute relatively easily the integrals that enter the game. But we will face another problem that I am going to discuss. So which is this other problem? Let me anticipate. The problem is that I can choose elements for the basis phi I running from 1 to n in a simple way. So I'm not really spending time in finding a special basis of eigenfunctions. But then, where do I spend my time? I spend my time in solving this equation here. Because in general, the matrix K is a matrix where all the elements are different from 0. It's not diagonal, and not even close to being diagonal in general. So it means that if I want to solve this problem, I have in general to compute the inverse of this matrix K, and this can be very time consuming. Just to be very concrete, in one dimension, things can be relatively easy, you know. In one dimension, after all, plenty of numerical techniques with whatever computer are fine. Let's say that in one dimension, we are happy in truncating our expansion on a base with 10 elements. Okay, that means that in general we will have to deal with a 10 times 10 matrix that we have to invert. It's not a big problem if we use a computer, we can do that easily. But imagine that instead of having a one-dimensional problem, you have a three-dimensional problem, and you want, so to say, to do the same. Okay, so you can easily imagine that essentially, that if you want to have a similar approximation, similarly good approximation, you have to use 10 elements for each of the direction of your space. I mean, the elements of your basis, for instance, you can imagine, I just take as products of functions similar one to the other, trigonometric functions, sinus function, but each of these sinus functions will contain either x or y or z. So I will have 10 times 10 times 10, so 1,000 different elements of my basis. If I want to say to approximate the solution equally well in the three directions. So now my matrix K has already become 1,000 times 1,000. It's still doable on a relatively rapid computer, but you immediately see that it has become much more difficult numerically. So the problem that we are facing, I mean, we are essentially translating the problem that in the case of the Fourier analysis was, it is difficult to compute the eigenfunctions, and now it has become, it can be difficult to compute the inverse of a relatively large or maybe very large matrix K that corresponds to solving this problem. Okay. As you recall, I told that there are 3 ingredients in this finite elements technique, and we have not yet seen the third ingredient that we are going to discuss in a moment. The third ingredient is the magic ingredient that will allow us to simplify significantly the problem, reducing ourselves to some matrix which is almost diagonal. Okay. But for the moment, we are not yet there. For the moment, just using the reformulation from strong version to weak version and just introducing a projection, okay, we have reduced the problem from an infinite dimensional problem to a finite dimensional problem, but still we are dealing with a space, the space, I mean, spanned by the matrix K, which can be very large in general. Let me just spend a few words on this point to be slightly more clear. There's a couple of little examples of the book. Tomorrow, maybe I will try to come with some numerical examples with Python, but for today, let's instead do analytic calculations, so to say. So a couple of examples. Let's concentrate ourselves on a space which is L square 0, 1. So what I can do is to restrict myself, and of course, sorry, let's put the famous D, meaning that I am considering only functions U which are vanishing at 0 and at 1. Okay. So let me now introduce a finite dimensional basis, and this basis consists of something like sinus of pi x, sinus of twice pi x, etc., etc. Sinus of n pi x. Okay, so essentially this phi I of x are our sinus of I pi x with I running from 1 to n. Okay. So this is our finite dimensional basis. And now let's consider 2 different problems. The first problem is very, very simple. The first problem is just the usual one, is minus second derivative of u respect to x square equal to x, let's say. So we are working with these boundary conditions here, okay? And it is trivial to get the solution, you just integrate twice. The exact solution of this problem, I mean, if you integrate once, you get minus 1/2 x squared plus a constant. Integrate another times, you get minus 1/6 x cubed plus cx plus a constant. After you fix the 2 constants, so to satisfy this. So the exact solution is 1/6 x minus x cubed. Okay, this is the exact solution. So what do we have to do if we want to try to solve this problem using the technique did I tell that the technique that we discussed is called Galerkin technique? Galerkin. I don't recall if I told. Galerkin. So the technique of going from a space of infinite dimension to the subspace is what is called Galerkin technique. Okay. So what do we have to do now if you want to go to this Galerkin technique? Well, first of all, as you recall, we have to introduce this scalar product A. Let me remind you, this A corresponds to this object here. And this object, therefore, is made by using the function k. But in our case, the function k is just equal to 1. Okay? So it becomes very trivial. In this case here, we can just say that A of u and v is just equal to the integral between 0 and 1 of the u over the x, the v over the x, the x. Okay. So what we did a moment ago here was to say that we have to, first of all, to build a matrix, and the matrix is the matrix in which essentially we are using this scalar product between the two elements of the base. Oops. So let's go down here. So we can build the matrix elements. Let's call these matrix elements Kij, and they are defined as A of phi j phi I. And this is equal to the integral between 0 and 1, and okay, d phi j over dx, d phi I over dx, dx, where the phi are just the sinus functions. Okay, so it is clear that this is a trivial. This becomes cosinus. Okay, and okay, I skip the little algebra. It's not something so crucial. So you just compute from the sinus, you get the cosinus. So you have to integrate the product of two cosinus. This can be done analytically, and you get I square pi square over 2 delta ij. Why you get this? Well, so both the phi are sinus, the derivative of the phi are cosinus. They are orthogonal, meaning that if I is different from j, this integral is 0. So you get a contribution only if I is equal to j, and in that case, essentially you get this quantity here is trivial by using the fact that it is a cosinus square, and you just rescale out the parameters and you get that. Okay. So this is our matrix Kij. So notice that in this specific case, the matrix is diagonal. The matrix is diagonal. And if a matrix is diagonal, then it's extremely simple to solve the problem, because all what remains is just to project also the f function on the same base, okay, in order to build all these elements here. But this projection is also very trivial. So essentially we have fi, that in this case are the integral between 0 and 1 of x, which was our f function. Each of the elements sinus of I pi x integrated x. Also this integral is trivial, I don't do it, is just minus 1 I plus 1 divided by I pi. Okay. So you see at this point our equation, our matrix equation, Ku equal to F, is extremely simple because K is diagonal. Therefore, if K is diagonal, this reduces to the fact that I have just, let's say, Kii Ui equal to Fi, with I running from 1 to n. Because K is diagonal. Okay, I don't have to sum on the index j because the only contribution is I equal to j, and I get this. And therefore, from this, I immediately get the solution. Ui is, of course, equal to Fi divided by Kii, and this is something, is whatever, is 2 minus 1 I plus 1 divided by I cube pi cube. So at that point, you have your solution because you have your Vn, which is written as usual as the sum on I running from 1 to n of Ui phi I. Okay. And this you can plot, maybe tomorrow we can again play a little with Python. So we can again try to do some of this numerically. It was perfectly fine. Okay, why it is so extremely simple? Exactly because our matrix K is diagonal. So I did not need to really compute the inverse of a matrix K because it was already written in a sense. Also, we can notice that this series is going to converge very rapidly. Why? Because notice that the coefficients, they go as 1 over I cube. So they get rapidly very small, increasing the value of I, and therefore increasing the value of n, which is the maximum value of I. And this technique is, in practical terms, completely equivalent to the Fourier analysis in this case, because of course, in this specific case, these functions, the sinus functions, are also the eigenfunctions of the differential operator. So, I mean, I've just rewritten essentially the same problem in two different ways, but essentially ending up with the same technique, because these functions, sinus functions, are also the eigenfunctions of the trivial operator, and the problem is just the same. Second example is what happens if I slightly complicate my life. So instead of having that equation, let's now consider the following equation. Minus derivative with respect to x of 1 plus x du over dx, and still equal to x. So the only difference respect to the previous case, in the previous case, k was equal to 1, and now this k is 1 plus x. Okay, that's it. That's the only difference. Okay. With the usual boundary conditions, u of 0 equal to u of 1 equal to 0. Okay, but the rest of the equation is just the same. So first point, if I wanted to solve this equation with the Fourier technique, the problem would be, it's not trivial to find the eigenfunctions of this differential operator. So in that case, the problem would be, which are the eigenfunctions? They are not the sinus functions. Okay. So let's keep the Fourier technique. Let's use this new technique. The new technique is, okay, I use my basis, phi 1, phi 2, phi n, so I don't need to evaluate to find the eigenfunctions. I just choose a basis simple basis, and that's it. Yeah, but in this case, what happens? I have again to evaluate my matrix element, my chi ij, and as you recall, the chi ij are the integral in this case between 0 and n of the elements of the basis, the derivative of the elements of the basis multiplied by k. So essentially the integral is 1 plus x, and what I have here is again something as d phi j over dx, d phi I over dx, integrated dx. So the integral is still very easy to do, because of course these are again the two cosinus. I just have to integrate cosinus 1 plus x. This can be done numerically. Actually, something that we should try to find out, I mentioned it to you. I mean, when I was using, Mathematica program, this type of integral could be done just pushing a button. But I mentioned to you that even inside Python, there is some package that allows to do some limited amount of analytic calculations. So I have already shown you that it's possible to solve, for instance, that simple ordinary differential equation analytically using Python, no? And I know that this type of integrals can also be performed using Python. The only problem is that I have not yet fully understood how to deal, for instance, here I have these indexes I and J and blah, blah. I suspect that Python is not as versatile as Mathematica, and probably one has to choose explicit numbers. I suspect you have to put I equal to 3, J equal to 4, and see what you get. But maybe if you want to try to play, recall that there is that package that is called SymP, Symbolic Python. And I do not exclude that there are smarter ways to use it than what I have been able to find up to now. Okay, so maybe one can compute this in a smart way using Python. You can use Python to compute this, but up to now I suspect that you have literally to write, to put two numbers instead of I and J, and after it provides you the answer. Okay, it's fine, but maybe it's possible to do in a smarter way. Or we do by hand, old style, okay? And if you do by hand, what you discover is that in this case, this is no more diagonal. It's no more just a delta ij, okay? Because of course this 1 plus x mixes together elements. And so what happens is you have two cases. The case I equal to j, and you get something. I don't know if to write this, you can find on the book, you get something. And for I different from j, you also get something which is in general different from 0. Okay, the book you can find at page 178, there are these two numbers or whatever. I mean, it's not particularly. So, which is the crucial information here? The crucial information is that because K, this object here, was not just 1, okay, then the matrix is not diagonal. And we run exactly into the problem that I was mentioning, because of course, after I can proceed exactly as before, because for instance, the F is exactly as before, because I have not changed the F function, so this column is still exactly this one, okay? But now I also have to solve a problem Ku equal to F, but this, sorry. Somebody's calling me for slide, please. Oh gosh. Oh, okay, sorry. Okay. Come si fa a impedire alla Giorgio che faccia PIN? Vabbè, Adesso subiremo un po' di ping, avete pazienza. Okay, so the problem here is that the matrix K is not diagonal, okay? So you have to invert, and this, as I said, can be very time consuming, can be difficult even with some modern computer. If you can easily end up with an enormous matrix. I mean, just to provide you a trivial example, as you know, I am playing with these compact stars, and essentially you solve differential equations, similar to this in a sense. But how big are the matrices that in principle you have to manipulate? For instance, let's say you have an object which is of the size of, let's say, a few tens kilometers. Two neutron stars want to merge. And you want to have a moderate resolution, really very, 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 very moderate, of, let's say, 100 meters. Okay, you don't do a lot with 100 meters resolution. So it means that in one dimension, you already have something of the order of 100 points or a few hundred points in one dimension. Now you have to cube it. So already that means that you have 10 million points, but after you have to make it evolve in time, and so you easily end up with something which is to invert matrices of the order, in principle, of course, to invert matrices of the order of 10 millions times 10 millions a few thousand times. Can be time consuming, okay, even if you run it on a fast computer. So this type of techniques, I mean, are really useful because in real life problems, you can easily end up with very big matrices that after you don't know what to do. Okay, so what I told up to now is essentially that we are happy, but only partially happy. Okay, we are partially happy because I mean, as I discussed with you, in principle, we have solved the problem. And of course, if the base contains a limited number of elements, it's not a big problem to invert numerically the matrix K. But in general, it can be a serious problem. So we need to introduce the third ingredient in our analysis. Let me try to do this in the next 20 minutes, at least in part, and tomorrow we will discuss better. So which is the third ingredient? Recall a moment what we need. We need a basis, a simple basis, possibly a basis that is good at approximating our solution, okay? So that we don't need to use an enormous number of elements to approximate the solution. The trick is to find a basis so that the matrix K is almost diagonal. Okay, so why this is useful? Because if the matrix K is diagonal, we have seen that we don't need to invert K, okay, because the equation becomes trivial, just one element, one element, one element. But even if a matrix K is not exactly diagonal, for instance, as we will see in the examples we are discussing, the matrix K becomes so-called tri-diagonal, meaning that it's different from zero on the main diagonal and on the diagonal just above and on the diagonal just below. So if the matrix K is, for instance, tri-diagonal or similar, you can again solve your problem very rapidly without the need of really computing the inverse of the matrix K, which would be extremely time consuming. So what we are trying to do is to find a basis such that the matrix K is, let's say, tri-diagonal, as close to being diagonal as possible. Let me remind you just to put these things to title possible links. Of course, I could always, so to say, diagonalize K. How? If I find the eigenfunctions of the original problem. because in that case I have diagonalized a problem. But then I have to pay the price that it can be extremely time consuming to generate the eigenfunctions. Okay, so you see, we have just moved this problem from one place to another, and only now we are trying to lock it down, say, okay, let's see a concrete way in which we reduce the numerical complexity of the problem. So the idea is use a basis, simple, and such that the matrix is almost diagonal. How can we do that? So we want to find a good way of approximating our function. And now in the course we are discussing just one example, but this is really one example out of many, many possibilities. The idea is that you approximate your function as a superposition of what are generally called piecewise polynomials. Now we are discussing a specific case of piecewise polynomials, but these piecewise polynomials are polynomials, so objects that can be of order 1, order 2, order whatever, but they have a maximum value, okay? So it is either a plus bx or a plus bx plus cx squared, blah, 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 blah. Order n, okay, polynomial, you choose which is the order that you like. But the second point is that, sorry, these polynomials are truncated in the sense that we will assume as basis polynomials which are different from 0 by definition only between 2 points and exactly 0 outside. I mean, the example that we are going to discuss is extremely simple. The discuss is the following. The example is the following. We will have, let's say, this is x, and essentially the idea is the following. Let's take a certain range, a certain interval, let's say between 0 and L. And let's first introduce what is called a grid. So we divide this interval in this way, for instance, equally spaced. Not necessarily they are equally spaced, okay? There can be cases in which you prefer to have them not equally spaced. But for simplicity, let's say that they are equally spaced. So this means that, let's say, if I have a certain delta x, which is this interval here, then each of these points xi is okay. A in this case was 0, so xi is just I delta x, okay, something like that. So I introduce a grid equally spaced in this case. And so, as I said, the idea of this piecewise polynomial is to write a function which is a polynomial, but after to set this function identically equal to 0 outside of a certain range. So, for instance, the simplest possibility is the following. I take these 3 points here, let's say, and I build a triangle. Okay. Why I do this? So notice that essentially I am using as a basis linear functions. I'm just introducing as elements of the base an object that is made with 2 linear functions. It is linear from here to here, linear from here to here. It's exactly 0 outside of this range. Okay. And of course, I will introduce not just one of these objects, but an entire set of these objects. Let me just change the color. I can introduce an entire set of these objects. Another object will be here, and so on and so forth. Okay. Oh gosh. Okay. Etc. Because in that way, as it is intuitively obvious, I can try to approximate whatever function defined between A and B, in this case 0 and L, with the superpositions of these triangles. Okay. I'm going to be slightly more formal in a moment, but I think that intuitively it should be clear. I essentially introduce some trivial localized objects, which in this case they are linear, and I'm just saying, yeah, my function is a linear superposition of these triangles. Of course, as you can imagine, this, as you will see, can work, but not always we are happy with this type of approximation. Why not always we are happy? You can already see the problem. The problem is that I have introduced, for instance, a point here where the first derivative of a function is discontinuous. So, I mean, this essentially amounts, now we are going to see more formally, but intuitively I think it's quite obvious. This corresponds essentially to the following, that I will, let's say, this is my function x, sorry, function f of x. Let's say function f of x is whatever, is something like this, okay? Let's suppose that, okay, it's vanishing between at 0 and an L. And I have my grid. And this approximation essentially corresponds to doing the following. Linearizing the function like this, like this, like this, 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 and this. Now we are going to check that, but it probably is intuitively obvious. So it is clear that I can approximate better and better my function, introducing more and more elements in my basis, okay? But it's also clear that if I use these linear functions as a first example of piecewise polynomials, okay, in certain cases I can be happy. In other cases, I'm not happy at all because my approximation to the solution, for instance, have plenty of angular points where the first derivative is discontinuous. So as you can imagine, there can be situations in which this is completely not acceptable. So it is obvious that I can generalize this approach, and instead of taking something which is just a linear function, I could take a piecewise approximation in which I use polynomials of order 2 instead of order 1 or order 3. Sorry. Should I have some water after 2 hours? It gets a bit dry. The order 3 is very much used because the order 3 allows us to have, so this is order 1, the first derivative is discontinuous. Order 2, the second derivative is discontinuous. Okay. Order 3, the third derivative is discontinuous, but the second derivative is continuous. And as you can imagine, there are plenty of situations in which we like to have a solution where at least the second derivative is continuous. So these cubic piecewise polynomials are very common in usage. We are not really going to use them, but keep in mind that very often you will find things like we are approximating by using cubic piecewise. There is another technique that is very similar to this. We are not going to discuss it, but is very well known, which is called the technique of the splines. So these splines are very similar to piecewise polynomials. There is some minor technical difference, okay? And also there, these cubic splines, so you can sometimes read, instead of cubic piecewise polynomials, you can read the cubic splines. And the splines are very similar to a piecewise polynomial, okay? There is some little technical difference, the way in which you use the nodes of the grid, but okay, the idea is rather similar. Okay, so and after maybe I will stop, and maybe we can after go ahead tomorrow. So what are we going to do? We are going to use a very simple base, which is the one that I have drawn here. Which is the advantage? Well, this object, each of these objects, lives on a limited space. So, as I said, tomorrow we do it more formally, but just to understand, if I'm going to write something as this integral between 0 and L, k of x, and I have this object here, d phi I over the x, d phi j over the x, dx. Well, it is clear that this is not diagonal, but is almost diagonal. Why is almost diagonal? Because each of these animals is different from 0 only on a very limited range. So if I take, let's say, this type of linear objects, and I is 3 and phi is 6 or even 5, or simply this scalar product is already 0, because I am putting together two objects which are separated enough so that where one is different from 0, the other is 0, and vice versa. So I'm going to get an object which is almost diagonal. It's typically 3 diagonal with linear piecewise polynomials. And then the matrix, I mean, I don't need to really compute the inverse of the matrix. There are numerical techniques for solving our linear algebra problem, Ku equal to F, that if a matrix is, let's say, 3 diagonal, are much more efficient than to compute K2 minus 1. Essentially, the problem is more complicated, of course, than in the case in which the matrix is diagonal, but the number of calculations is much smaller than computing K2 minus 1. So this is the reason why we are going to discuss this type of piecewise polynomials, okay? And this essentially is what constitutes the technique of finite elements. So the technique of finite elements is let me tell again, I mean, first of all, we have rewritten our problem in that weak form. So, okay, we have introduced a sort of scalar product and blah, 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 blah. Still, the problem was complicated, and we say, okay, now we use the approximation of Galerkin, because we know that it's a good approximation. It guarantees us that we restrict to a certain subspace. The equation that we have written is the best approximation to the original equation within the subspace. Okay, still is not the solution of everything for the reason that I was mentioning, because okay, it ends up with having to determine, to find the coefficients of the expansion of a solution on a certain finite basis. But if the finite basis is very large, in general, you have to invert a very large matrix. That can be still a very tough problem. So the third and final ingredient is let's use a basis where that matrix is almost diagonal. Then it can be numerically very efficient. Okay, tomorrow maybe I can tell this slightly more formally, and we can play a little with some Python example. Okay, and I forgot to put, I will do today, I will put on this Google Class the 2 examples that we discussed before. Questions? Is it okay? Sì. Sì, vuol dire a pezzi, sì. And there is something that I think is, using Mathematica, there was a special command, so to say, ready, that was allowing us to write very rapidly a piecewise function. I mean, we will have to write something which is, as I said, different from 0 only on a certain limited range, and typically on a certain number of elements of the grid. But I checked, and I think that also in Python is already written some sort of little instruction that allows us to rapidly write these piecewise functions that will will make things a little bit easier. Instead, it's lengthy to define everything. But these piecewise functions, I think, are already defined in some little package of Python. Instead, one is to rewrite everything from scratch. Okay, questions from home?
No, it's all okay. Thank you.
Okay.
It's okay.
Then see you tomorrow then. Okay. Bye. Ciao ciao a tutti.
Arrivederci.
Recording.